Is infinity an odd or even number? 2011. In my experience with children, one of the easiest to grasp concepts of infinity is provided by the transfinite ordinals, since it can be viewed as a continuation of the usual counting manner of children, but proceeding into the transfinite. A plus A plus A plus A equals O plus O plus A plus A. Presumably this person has no experience with 6-year-olds. This explanation is horrendous, haha.
No, it isn't. If you ask a child what comes after infinity, infinity plus 1 is pretty much the default answer. Any kid who knows multiplication knows infinity plus infinity is the same as infinity times 2. The answer of infinity times infinity is also popular for kids to say when they know a number bigger than their friend, who just proclaimed infinity is the largest number.
I thought that most of us learn at an early age, as a result of this kind of exchange, that infinity is not the biggest number, or even a number at all, as far as the ordinary notion of number goes.
Any kid who knows multiplication knows infinity plus infinity is the same as infinity times 2. Or is it 2 times infinity? Hint: it isn't, because 2 times infinity equals infinity, while infinity times 2 equals infinity plus infinity. Not sure every kid knows that.
What? Where does that follow from? 6-year-olds know multiplication.
Some do, yes. If they have an aptitude for basic sums, then pointing out that 3 by 3 is the same as 3 plus 3 plus 3 sets them down the right path.
The technique used by the Oregon public school system in the 80s went something like, hand the child a 10 by 10 grid of numbers, then tell them, absent of any other context, that they must be memorized. I like your way better.
The way I would explain it to a 6-year-old would be like this. Infinity isn't a number really, it's a concept. Like the word many or the word few. If someone says they have many of something, you don't think is that odd, or even you just know they have a lot of it. Infinity is kind of like that. It explains the idea of things going on forever, not an exact quantity of things like the number 10 or 11.
My 6 and 7-years call infinity the endless number. Well, at least it is a Nan number. P.S. They seem to know that star endless, greater than endless, but do not dare to admit it.
Well, that fear is good, because multiplication won't change the cardinality. You have to go exponential.
There is a difference between infinity and not a number. Nan isn't event equal to itself. In nodies you get infinity plus infinity. 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 Nan. Infinity equals infinity. True. Nan equals Nan. False. The fun thing, Nan to the power of 0, because technically the type of Nan is a number. Star star 0. 1. Type of Nan. Number. By the same logic, Nan is also even because Nan plus Nan. Nan. But I think it's better not explain that to your 6-year-old.
Infinite is just a fancy word for endless anyway.
Not necessarily. A circle is endless, and yet certainly isn't infinite.
The way I would explain it to a 6-year-old would be like this. There are natural numbers, like and so on. Natural numbers can be odd or even. There is no such natural number as infinity. Therefore, the question if infinity is odd or even is meaningless. It does not even type check. In math, people like well-formed questions, and generally don't like ill-formed questions.
So there seems like a glaring hole in the answer, but maybe I'm missing something. Because it is easy to prove from this definition, by transfinite recursion, that the ordinals come in an alternating even-odd pattern, and that every limit ordinal, and hence every infinite cardinal, is even. Sure, if we use the natural numbers and start at 1, then we can group 1, 2, 3, 4, 5, 6, and prove infinity is even. But we could also just as easily group 1, 2, 3, 4, 5, 6, 7, and prove infinity is odd. It's the same if we try to split into 2 equal subsets, because we can split into 135, 246, and say it's even. Or we can divide 1, 246, 357, and prove it's odd because we have 2 equal subsets plus 1 left over. So I'm missing the reason for why the second versions aren't just as valid. Of course, I'm more inclined to agree with many commenters here that it's just a category error, and asking whether infinity is even, odd, is as useful as asking whether democracy is blonde or brunette.
I would weaken the definition of even odd to say that a set is even if there exists a way to pair things off, and odd if there is no way to pair things off, i.e., not even. So the countable numbers would be even.
To explain the idea to a child, I would focus on the principal idea. Whether finite or infinite, a number is even when it can be divided into pairs. For finite sets, this is the same as the ability to divide the set into 2 sets of equal size, since one may consider the first element of each pair and the second element of each pair. The answer this quote came from is amazingly obtuse, but it does make me think that infinity must be even since infinity can be divided into 2 pairs, each of which is of equal size, since both are infinity.
Infinities aren't comparable for equality, are they?
I want to know if there are more decimal numbers between 0 and 1 than there are integers between 0 and infinity.
There are, and it turns out that this is a significant mathematical concept. The integers between 0 and infinity are defined as countably infinite. Other infinities are considered countably infinite, or the same infinity, if and only if you can arrange it in a list, such that each item in the list pairs to an integer in our 0 to infinity list. So the set of even numbers is countably infinite, because for every of that is an even number, it pairs with the number I2. To demonstrate, 0 greater than 0, 2 greater than 1, 4 greater than 2, 6 greater than 3. The decimal real numbers between 0 and 1 are not countably infinite, and we know this from a concept called Cantor diagonalization. What Cantor did was a proof by contradiction. Assume that the numbers are countably infinite, then you can arrange them in a list. However, he then builds a number by altering the first decimal place of the first number, the second decimal place of the second number, and so on. Finally, he shows that this built number is both a real number and is not on the list. Therefore, the real numbers between 0 and 1 cannot be ordered into a list, therefore they are not countably infinite, and there are more decimal numbers between 0 and 1 than integers between 0 and infinity.
Countably infinite makes 0 sense to me. Whatever method you use to generate your decimals, you can just slap an integer on each step of the way. You'll never run out of integers. I'll put Cantor and his proof in a box, tell him to give me his fancy decimals quick as he can, and I can match each one with an integer no problem. And pairing one infinite list with another infinite list doesn't make either one any more countable, because however high you count, they keep on going.
Whatever method you use to generate your decimals, you can just slap an integer on each step of the way. You'll never run out of integers. Exactly correct. This holds true of everything you can generate stepwise, even infinite sets. Cantor proved that you cannot generate, stepwise, all rails between 0 and 1. Any infinite set you can generate stepwise is countably infinite. I'll put Cantor and his proof in a box. Tell him to give me his fancy decimals quick as he can, and I can match each one with an integer no problem. Exactly correct. And then infinitely later, when you're done, having generated every real between 0 and 1, he will then generate a new real not on your list. Oops! You have not generated all rails between 0 and 1, even with infinite time. And pairing one infinite list with another infinite list doesn't make either one any more countable, because however high you count, they keep on going. Exactly correct. Any 2 sets you can pair together, via a bijection, have the exact same cardinality. Neither is more infinite nor countable than the other. Cantor proved you cannot pair the rails with the natural numbers. You and Cantor agree completely. You're very close to understanding why the rails are bigger.
Depends what you mean by decimal. Decimal is a system of notation. Does it count as a decimal number if it cannot be written in decimal notation in finite time? If not, then they are equal. If yes, then there are more decimal numbers between 0 and 1 than integers.
I don't usually use that term, but I take it to mean number you may, and if not using e.g. fractions, must write using a decimal point, because that seems to always be what people intend by it. Everybody experienced writing irrational numbers using decimal notation in school, so those definitely count.
The correct mathematical term is real number.
Yes, but you'll see decimal more in the wild, and that's what people mean by it. You write it with a decimal point, and they do usually mean to include the irrationals. So yes, real numbers, but the reasoning behind their usage is you write it with a decimal point. I bet more people understand decimal number used in that sense than understand real number.
I've never seen an irrational number written in digits in my whole life. Have you? I've seen them expressed as letters or formula.
To explain to a 6-year-old, I would start by telling them that there are many different kinds of infinity, not just one. Some infinities are odd, others are even, and others are neither. It matters whether you are asking how many cardinals, or in what position, ordinals. For regular finite numbers, cardinals and ordinals are more or less the same, but for infinities, they behave differently. Then, if they want to get into the weeds, you can introduce them to transfinite ordinals, diagonalization, and all that fun stuff.
Infinity is equal to the product of all the primes. It is even because it has 2 as a factor.
In JavaScript, we're spoiled by having both. There's number, negative infinity, and number, positive infinity.
I really hate these mathematical technicalities, spawned from material implication, chosen way of making a definition, and vacuous truth. Why can't we even consider some questions to be marked as nonsense, non-relevant like in relevance logic?